like this is going to be hard for you too, what I'm about to do, but I don't want to dampen your like joy. That's mostly it. So please ride the joy. All right, let's settle in, friends. And if you're not participating, please just try to stay still and do nothing and veg out. Take a tiny nap. Whatever works for you. Just settle in. And tune into your breath. Without forcing or controlling, just letting go. Simply observing. You can make a little challenge for yourself. Can you completely observe your breath through the start to the end of a cycle without drifting off into thought? That can be quite challenging. If you fall off or thinking about something else, just start over. No blame, no guilt. As we bring it to a close, think of something you're grateful for. There must be something. We're all here and able to walk. There's a good start. Pick a little smile in your mind. Come on back. Some calculus time. I got really scared when I said we're all able to walk, and then I started like rolling through my head like, oh shit, wait, everybody can walk in here, right? Okay, good. Whew.
Start the recording.
What's that?
Did you start the recording?
No, oh God, you scared the hell out of me. I thought you were saying you forgot about.
No. I didn't say that.
You forgot about the person in our class who has a wheelchair. Yeah, I did, thanks. Now that's all on there, that's great. Good. New WebWorks though opens at 12:15 today. It's small, but don't wait until the last minute. I mean, that's my message. I would say it would be awesome if we could talk about this on Friday when we get together, my friends. So let's kind of talk about the types of problems that will be on there. A little bit of a warm up and just refreshing some of the ideas. So let's say I've got some object and I have observed it at these various times. So this is time in seconds, and then this is velocity in feet per second. And I've got 4 observations. And so at 0 seconds, which is when I started my observations, not necessarily, this thing wasn't suddenly, for no reason, cruising at 90 feet per second. I just started noticing it. Then, 2 seconds later, it was at 46 feet per second. 4 seconds later, 17 and 6, 0. It came to a standstill after 6 seconds. Figure, whatever your favorite thing. Maybe you hit the brakes on your car. 90 feet per second. Oh shit, I got it. I just got to know how many miles per hour that is. Let's just do that really quick. So 90 feet per second. So we want to go to miles per.
5280.
What is it? What?
Well, a mile is 5280.
Yeah, 5.2. Yes. So this is going to be divide by, so 1 foot. No, wait. 5280. Wait. one mile. 1 mile. There we go. Per 5280 feet. Yeah. And then 3,600 seconds in an hour. So 3,600 seconds per hour. And could somebody? That's actually not that fast. Could someone actually just multiply 90 by 3,600 divided by 5280 for us, please?
It says 61.
Nice. Wow.
61.36.
61.36 miles per hour. That's cool. All right. Completely reasonable. Shockingly reasonable, because I just made this shit up. So, my question to you is, can you give me 2 estimates on the distance traveled in those 6 seconds? And let me do the underestimate for you, and then you can do the over. So let's find an over and underestimate for total distance traveled. First thing I would do is draw a picture, for sure, just to make some rectangles, because that's what this is all going to be about. So at 0 seconds, I'm at 90 feet per second. So let's see here, 0, I'm at 90. Well, let's make that bigger, because we go down from there, right? So there's 90 feet per second, and that's the time I observe, or the velocity I observe there. 2 seconds later, I'm at 46, which is just almost exactly half of that distance. So that's going to be, I'll put that right above there. This is a nice way to write these when you're making these pictures. Just put the value on top of the data point. 4 is going to be 17. That's like a third-ish, not quite. I think so, like a third of this shit. That's fine. That's enough. No brain surgery happening here. 17 and then 0 I got. Right on that one. Nice. That looks hella linear, but maybe it was meant to be. I don't know. Yeah, that's why I want to drop this. There we go. It's not supposed to be linear, and it is. Okay. So how do I get that overestimate? Well, I take my samples as a representative for an entire interval. So all I know is the time right here at 0 seconds for, what am I going to do? I'm going to do the underestimate. So I'm going to assume, I'm going to use the ending velocity, so for the underestimate. I'm going to use the ending velocity as a representative of the velocity over the previous 2 seconds. So that means what I'm going to assume is that in this first 0 to 2 seconds, I was traveling 46 feet per second. For the overestimate, I would assume it was 90. Notice how I'm totally ignoring that original data point. And then over the next 2 seconds, I was traveling 17, and then I just stopped traveling for that last 2 seconds. Now this is obviously not accurate, but that's okay. We're doing an estimate with what we can. So all I have to do is realize that if I was traveling at 46 feet per second for 2 seconds, that's the area of this box, and that area is 92, thank you, yeah. So let's write this up here. Let's call that area 1, area 2, and then I'll write area 3 here, even though we can see it's 0. So our estimate is going to equal area 1 plus area 2 plus area 3. Let me stop here because it's absolutely essential that you understand why it's the area. So if you don't, let's talk. That's really, that's fundamental. That you understand why the area of that rectangle is the approximate distance traveled. And it's because velocity times time is distance if the velocity is constant. Right? Look at how those units cancel. 46 feet per second times 2 seconds. Units cancel. Gives me my total distance traveled. So is everybody cool on that? Yeah? All right. All right, great. Because this whole thing, the rest of the semester is about rectangles. It really is. Ooh, this is a nice comfy knee rest here. So my estimate's going to be the sum of those 3. So that's going to be, let's write this out in a neat way. It's going to be 46 times 2 plus 17 times 2 plus 0 times 2. So I'm taking height times base, And so then, let's see, Alex gave me that 92 plus 34 plus 0, and that is 126 feet. So my question for you is please give me an overestimate. Cool. Find that overestimate. I'm just getting a picture up here. So you got a web word problem like this, right? It's easy, but you got to know what to do. Did you get one?
Yeah, I got that bottom one. It's the
Nice.
top one against the average.
Nice, thanks. That's great. That average worked out pretty sweet. You're doing good, man. Yeah, beautiful. Good back here, friends. Yeah. Nice. Good, Joey. Good. All right.
These are doing good. This is making sense. Okay, great. Are you good here? Yes.
Yeah.
Okay, those make sense for me.
So just go to the picture. If we're going to do an overestimate, so now assume it's the highest velocity for that time. So for this first 2 seconds, assume you just stayed at 90. Okay. And then assume you stayed at 47, and assume you stayed at 70. So 3 different, right? Does that make sense?
Yeah.
Yeah, that's the way we roll. How's it going? Looking good. Yeah. Nice rectangles.
46, I don't know, 47.
Yeah, I know, I was like, something changed. Okay, thanks.
It's 46.
Thank you.
So it's
Yeah.
gonna be 92.
That's funny, because I was thinking, wasn't that 92 before?
But then I looked up, I was like, your math is correct.
The math is correct, my recollection is quite faulty, and so then that gives me
306.
306. Does this sound good? We do this, we understanding the concept. I know you can multiply numbers together and add them. You're in Cal. But understanding why you're doing that, that's the key thing. What would be, so this is way under, obviously. That is way over, maybe not as obviously, but what could we do to find a middle ground, Alex?
You add them together, divide by 2.
Find the average. So an average would be maybe a nice, better estimate. So the average equals a better estimate. So that average is going to be half of the underestimate plus the overestimate. And Alex, you worked that through, sir?
216.
216 feet. Thank you. So the Babylonians were doing this. This is an ancient thing. This is part of who we are. This is part of humanity is thinking like this. Part of interacting with the universe. Is there any questions on that, friends? After I've just told you it's should be an innate part of who you are, like breathing. Are there any questions? Okay. Let's take a look at a slightly different problem. Now, so this one, we didn't see anything like this last time. So suppose I know the velocity function. The velocity at time t is 11t meters per second. Find the exact distance traveled from 0 seconds to 10 seconds. So find the exact distance traveled. We're going to do this 2 ways. What did I say, 10 or something? 10, yeah. Excuse me, let's draw a graph of this. So here's v of t, and that's a line with slope 11. We're going to make it look very diagonalish just for convenience. But there's 10, and then when t is 10, that's 110. So this is 110 meters per second, not feet or anything. That's my velocity at the end. Started from a velocity of 0, ended up cruising. And that's probably really fast. This is like over 180 miles an hour if our previous computation, right? Because there's about 3 meters in a foot. So this is like 330.
There's 3 feet, you mean 3.2?
What did I say?
You said 3 meters in a foot.
Sorry, yeah, 3 feet, about 3 feet in a meter. So this is like 330 feet per second.
And the last one was 90s.
And the last one was 90, and that was 60 miles an hour. So
yeah, 200.
Kind of cruising out on the mountain road, hoping there's no fuzz waiting around the corner. And whatever it is you drive fast, you don't drive my shitty purple Subaru Forester at that velocity. Okay, cool. So let's do this a way we haven't even talked about before. What is the relationship between position and velocity? What is the relationship between those functions?
Velocity is the derivative of position.
Absolutely, yes. Thank you, Nina. So we know that the derivative of position is velocity. So if I could find an s of t whose derivative was 11t, I might know something about the position. So let's find s of t whose derivative is the velocity function. And this is linking up something very powerful and really important for the rest of the semester. I guess I gotta stop saying that, because everything we talk about is important for the rest of the semester, because it is the rest of the semester. It pretty much is. So I need a function whose derivative is 11t. Can anyone maybe help me out here? Nina, oh, Nina, yes, sorry. Nina.
No, okay.
Do you wanna go?
Hold up, I can just. It would be 5.5t squared.
Is that what you're gonna say? Yeah, yes! Hell yes! So check it out. So the proposal is that S of t is 11 halves t squared. Because Alex is doing the power rule backwards in his head. And he's thinking, if this is the derivative, it must have come from a t squared thing. Right? So now we're turning everything we've done backwards. We're doing derivatives in reverse. We're finding the thing that the derivative came from. It's gonna be all right, Joey. We're gonna have all sorts of rules. It'll be cool, man. So we did this backwards. Are there any other answers?
Couldn't you add any constant?
Yes. Did you have calc before? Oh, that's so good. I was thinking your teacher was like, put plus C, because I'll be saying that.
But don't use k as a constant, or does it not matter?
You could use anything you want as a constant. The classic for calc is a plus C. It's just like, it's not wrong to put whatever you want. So if you want to be creative, go for it. Just let me know that that's what's happening. So this could be any function here. Notice that the derivative will be the same because this goes to 0, right? This will die away. So there's actually infinitely many answers. Infinitely many possible S of t's. Because of that constant. I can put 10 there, -3 there, whatever, a pi, 0. But here's the good news. No matter what it is, the change in the distance traveled is going to be, so how about this? We say distance traveled, let me write this out. Distance traveled equals ending position minus starting position. That seems fair, right? Where did it end up? Where did I start? That's the total distance I traveled. And so that's going to be the position at 11 seconds minus the position at 0 seconds. What is it?
10 seconds.
10. Thank you. Thanks, Kidra. Yes. Thank you, man. Yep, 10 seconds right there. So check it out. I'm going to plug that in here. So this is going to be 11 halves times 10 squared plus c. Notice how I'm just pretending it's going to be okay, because it is. 11 halves times 0 squared plus c. What happens to those c's? They cancel. So it never really mattered what we put. It would have canceled out when we did this difference. So this turns into, this is dead. This is nothing. So this is 110 halves. That is 55 meters. That's the precise distance traveled. So let me stop for a second, let that just kind of soak in. Let me know if there's any questions on it, because I want to link it to something we talked about on Monday. Is this all good? Feeling good? All right, cool. So, on Monday, what we did was we took the shape. We had a parabola, right? Do you remember I did the parabola example and I found the area under there precisely? And the name of that game was to cut this up into little rectangles, arbitrary number, and find the area of the approximation depending on the number of cuts, and then we let that approximate area estimate go to whatever it went to as the number of cuts went to infinity. What it amounted to was just the area under this curve. What is the area under this curve?
1/3 for x squared. Oh, that's for x squared, but
Yes, no, yeah, it's just for a triangle. What's the area of this triangle?
1/2.
1/2 base times height, right? So area is 1/2 base times height, and notice that is precisely 55. Here's the base, it's 10, height is 110, so that's 1/2 10 times 110, oh shit, that's 55. Just like that gave us.
Wait,
This-
what? 1/2 of 10 is 5 times 110 is 550.
What, wait, did I do, what
550.
what did I do wrong?
It should be, 1,100 over 2 on the right side.
Yes, over
Because
here.
10's
Oh,
squared.
God, thank you. Okay, I lost a 0, shit, okay, sorry. That, we add a 0 there, toss a 0 here, cool. So, the point I wanted to make was that the area under this thing, which is the total distance traveled, is equal to this antiderivative evaluated at the endpoints and the difference of those two results. So look at how this works. One way is totally geometric. Find the area under a triangle. 1/2 base times height. That gives the same answer as calculus gives in reverse when we do reverse derivatives. Same exact answer. And this is hinting at what's called the fundamental theorem of calculus. So the other way I want to put up here, let me summarize this for you, is find the area under the velocity curve and above the x-axis as well. Because otherwise it just like falls down to hell. The area is infinite. So we got to cut it off somewhere. We cut it at the x-axis. Find the area under the velocity curve, and this gives the exact distance traveled as well. AKA 550 meters. It's kind of amazing how that worked. It's really crazy that the calculus is linked, the derivatives are linked to this whole process at all. Seems quite amazing. So, let me put here, this is an example of the fundamental theorem of calculus. Part 1. There's another part, but that we're not going to be ready for part 2 till Monday. That's like a Monday kind of thing. You got to be fresh for that. Seems crazy that last 3 weeks of class we're talking about the fundamental theorem of calculus, but to understand the fundamental theorem of calculus, you need 3 months of calculus. It's just the way it goes. So let's take a look at an example that's a little trickier and also much like a web work problem you may encounter in the next several days. So let's take last example. Oh no, here, okay, maybe 2 more examples, what the hell? So the velocity of a particle moving on a line, moving on the x-axis. So it's just on a line, right? Here's my particle. It lives on a line, and I can figure out where it's at by its relationship to whatever I call 0 on that line. The velocity is given by v of t equals 12 minus 4t. Find the exact distance traveled as t changes from 0 to 4 seconds. So this, let's say this is in meters per second. There's step one, look, what do I have? A graph. If nothing else, if you take nothing else from this class, when you're doing math, when you're trying to think about functions, get a picture. That's a great place to start no matter what you are doing. So here's v of t, here's t, and I got a nice old line with a y-intercept of 12. When t is 0, I'm at 12 meters per second. When t is 3, I'm at 0. When t is 4, I'm at negative, so it's 12 minus 4, negative 4. Here, here's negative 4 and 4. So that's my velocity curve. What is this particle doing? What is the movie of this particle? Here's the line.
Is it moving from right to left?
It is, well, so right now, right here, it's got a positive velocity, right?
Yeah.
So that's moving from left to right. So right now it's going 12 meters per second to the right, and that is diminishing. What does it do? So it's slowing down, right? So it's, what happens?
And then it starts going the other way.
And then it starts going the other way. At 3 seconds, it stops and backs up for about a second. Right, so you see that? It's super fast, slowing down, hits 0 at 3 seconds, has a negative velocity, so it backs up a little bit. So the particle, again, and I don't know where it's starting. Look, I don't even know where its original position is, so I just have to imagine. Let's say it's right here. We cruise this way, slow down, and then back up just a little bit. Well, let's roll with our idea, though. It's just the area, dude. It's just the area. Distance traveled is just the area. So S of t equals the total area under this curve. But some of that area looks negative and some of it looks positive. And that's okay, because I do know I'm going backwards. So this area here, first off, let's see here, that's area 1. Let's call this area 2. Notice area 2 will be negative, which makes sense because I'm losing position. It better be negative. I'm backing up. My position needs to diminish. So this area here, area 1, is equal to 1/2 base times height, so 18 meters, plus, besides area 1, area 2 is going to be negative.
1/2, right? 'Cause it's,
Yeah,
or no, just kidding. It's going to be negative 2.
beautiful. Negative 2 meters, because the height is, this is 2 here, right? So how far do I travel?
20 meters.
Nope.
16.
16, because this is negative, so careful. Be real careful, because we backed up, right? So at this point, when we got here, this was 18 meters. And then we lost velocity, or we turned around and went back. So this is the retracement of 2 meters worth of that path. So always add the areas and always sign the areas. So think of this term, signed area is going to be your friend.
Wait, so then it's technically not your total distance that
Yeah,
you
because you said
traveled.
exact distance traveled. Which it,
Oh, I see
you
what
would-
you're
You
saying.
would say like the
Yeah.
exact distance between a starting
Yeah.
point and end point, right?
So it's like the distance.
It's
You-
distance between.
Was it you that said 20?
From the beginning,
So-
looking at, like, the space between.
You're right. So yes. So the I guess what I'm saying is the total displacement. Maybe that's what I should have said. So listen, check out what Nina's pointed out here. Nina said total distance traveled is 20. That is correct. My language was bad. Because I did go 18 meters this way and then I turned around and walked 2 meters this way, or whatever. So total distance is 20, the total displacement is what I'm looking for. So total displacement, thanks Nina, is going to be 18, then minus the 2, so 16 meters. You're 16 meters away from where you started, 16 meters to the right of where you started. That's good, that was awesome. Very nice. Now let me give you a problem. Here's a velocity function. Tell me the total displacement. I've learned my lesson. So find total displacement. Here's V of t, and sure, meters per second, why not? Doesn't matter. Make up your favorite. Not cubits. Yeah, cubits per century. You know, come up with whatever your favorite units of travel, distance, velocity are. And here's time. I'm just going to use something standard so we don't get too crazy. Meters per second. So this is 5 meters per second for the first 2 seconds, constantly. That's 2 seconds. I'm traveling that fast at 5. Not accelerating, not decelerating. Between 2 and 3, the velocity drops to 0. Between 3 and 4, the velocity drops to -3. So this should be -3 right there. And then from 4 to 5, it goes back up to 0. And then for the last second, it goes up. So to 6 seconds, there we go. And yeah, let's see, so that height there is, well shit, it needs to be proportional, so I guess that's 3. You know. Please assume everything's straight lines and rectangles and triangles. Find the total displacement. I need to change that in my notes, Nina. Good. Yeah. Okay, I think it's up. Yeah, Isn't it soothing to just add areas? So you're gonna find the areas made with the x-axis. When it's under, it's a negative area. So you just need to find the area of that minus the area of that. Area of the triangle is base times 1/2 base times height, no matter what the triangle looks like. And the area of the rectangle is just base times height. So what's the area of this first bit? No, so right there, let's stop there. Just that rectangle, that's the area of the rectangle. Yes, ma'am, yeah, sorry, yeah, yeah. Nope, how high is it?
Yeah, the whole rectangle, because the top of the curve is 5, right? So what's the area of that rectangle? Almost. How wide is it? Yeah, it's 5 times 2. There you go, it's all good, it's all good. Yes, yes. So this is 10. So in this time I traveled 10 meters. Then what is now, let's go to your friend here. What's the area of that triangle right there? Yeah, there you go. So now I traveled 2.5 meters. What am I doing here in this next little window? What's the height? Got 11, left, your unit, left, with 10, that triangle. It's -3, yeah. This is gonna be a negative area, right? That makes sense. So what's the height? 3. Then what's the base? So 1/2 base times height works no matter what the triangle looks like. So. Yeah, does that make sense? So I'm really just like thinking triangles and rectangles, because those are the only two things I know how to. There you go. Yeah. Perfect. You good? I think so. What did kids forget here? You got 11? Oh, yeah. So it's where you forgot the back up. You got 11.
Yeah.
You got
11 cubic.
We should be getting 11. How's that going? 11 shaking out. You got 15. Let's check it out. So how did you get? Yep. Oh wait. So check. So just 5 to 2 is that? Is that? Yeah, yeah. Your picture was like, I was looking at your picture. I was like, that looks confusing. Yeah, yeah. So it's just a rectangle on T from 0 to 2, and then the rest is a bunch of triangles. Does that make sense? Okay. Ariane, how's this going? Making sense? Did you get 11 like a million years ago? Yeah. Yeah, does this make sense from?
Oh, that's right, so it's area of this.
Yeah. Perfect.
And area of this triangle.
Beautiful. Yeah, this is great. And then minus the area of that little triangle underneath. Yeah.
And this one would be minus as well.
This one's plus because this one's above, right? So if you're below the x-axis, show me the one you were thinking of, because I think you might be looking at this in an odd way. Show me the triangle.
So
you
the
were
triangle
thinking.
is this one here?
Oh, no, no, no.
Oh, is it this
Yes,
one here?
yes, yeah,
Oh,
there you go.
oh.
That's okay. I'm glad we checked. Yes. It's looking good. You're doing good. You're holding off on that negative. Yeah. Carly, we good? I think we are. Indeed. Joey, how's it going for you? Solid.
Wrong.
No, man, that's great. That's great. So, it's just a triangle. What's the base? 2 across. And then what's its height? There you go. And just use 1/2 base times height. No matter what your triangle looks like, that always works. Yeah. Negative. Because it's a negative area. Yeah, so it's a negative area. It's because you're backing up. Now you got it. And just find that and add them all together. Friends, how's it going back here? Nice shading. Nice shading. Oh yeah, and you're solid too. Yeah, look at that shading. Holy shit. Come back here to get shading. Beautiful. Yes. Yes. I know you two got it. Alrighty, friends. Seems like everybody is cruising here. So just remember, break everything into rectangles and triangles if you were to encounter such a thing in web work. So this area here is just going to be 5 times 2. That's 10 meters I traveled there. Here it's base is 1, height is 5, so this is 2.5. 2.5 meters. Oh, good lord. 2.5 meters. In here I'm backing up, so I may need to keep that in mind and understand this is a negative area. Its height is 3, and its base is 2. So -3 is the total area. -3 meters were traveled in that time interval. And then out here, just got a height of 3, base of 1, so 3/2. 1.5 meters, I think. Yep, yeah, cool. add up all the results. So 15.5 minus 3,
No, it's 2.5 plus 1.5, which is 4.
13.5, yeah.
Yeah, so 2.5 plus 1.5 is 4, plus 10 is 14, minus 3 is 11.
Oh shit, yes, good lord. Yeah, so 11 meters total.
Yeah.
Okay. Let's actually talk about the thing Nina said. What's the total distance traveled if we were actually like we had our odometer on our car? 17, so I would add this, right? So total distance traveled, so this is net displacement. Let's actually write that in your notes, because I think that might be on the web board as well. And then total distance is equal to
14, I think.
14.
Right?
No, it would be
No.
17.
Why 17?
Because 10 plus 2.5 plus 3 plus 1.5.
Yes, thanks. And I'm just like up here, like just doing what Alex does. Tell me what to do, Alex. But yes, because you subtracted off 3 to get this one from the original total, Alex, you actually have to add double that. Does that make sense?
Sure.
Yeah. So 17 meters. Thank you. Thanks, everyone. Bless you. All right. Questions on that? I got one last thing to show you today. This is the heaviest thing I've shown you all semester.
What you're about to show us, or
What I'm about to show you about. Yeah. It's one of the most beautiful things, too. So let's just make sure we're good with that. I want to introduce a little bit of notation before I go on. So this is summation notation. We have to have a new way to write arbitrary sums of things, because as you see, we've been adding things like crazy. And so this whole thing is about adding arbitrary quantities. So first off, if you see this symbol, and we are speaking mathematics, this is a capital sigma. Lowercase sigma is this one. It's used in statistics a lot for standard deviation and variance and stuff like that. We stick with capital sigma. It's the Greek S, and it stands for sum. So it makes a lot of sense. It's where we got our S from. So when I see the symbol, I immediately know that something is being summed up. When you see this, it's a sum. It will have an index associated with it. So here I could put I equals 1, and so this is the index, that I, that variable, could be any variable. This is the starting index value. And up on top, here, let's just give a nice solid example, put a 4 on top. This is the ending index value. So right now, what I know is that this I value is going to run from 1 to 4, and I assume it moves in units. So when I see this thing, and you might want to put a little note here, we know that I runs from 1 to 4, from the starting index on the bottom to the upper index on top, by ones. So in other words, I is going to equal 1, 2, 3, 4. But I don't have anything to add yet. So that's why I put something here. Let's say this is just some function of I. So when I write this, this is some expression in I. It could be I squared, it could be 3I, it could be much more complicated than that. But just note that this is an expression with I as a variable. And when I write this, this is just shorthand notation, meaning that I'm going to let I run from 1 to 4, and I'm going to plug each value into that expression. So first I is 1. then I is 2, and I'm going to add the results. Then I is 3, then I is 4. And so this is shorthand notation for this down here. And we'll do some examples to make sure this. We might not actually do the heaviest thing we have to do today. We might just let this get in our brains and sit and stew till Friday. So for example, if I said sum I equals 2 to 5 of I squared. This is shorthand notation for the following sum. First I is 2, and I square it. So it's 2 squared plus 3 squared plus 4 squared plus 5 squared. Pretty compact. And this one I can actually do. Let's see. So that's 4 plus 9 plus 16 plus 25, all those beautiful perfect squares. And we've got 13, 29, 54. Somebody check me out. That, please. Yeah? Okay. Good, good. So this just represents a sum which can be added up to this. What is this? Can someone tell us what that is? That would be great. Breakfast is wearing thin, starting to get weak. And I don't need the sum. Can somebody just tell us, like, what does the sum look like?
1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10.
Beautiful. It's 55. Good song. And it's going to be 55 when we add it all up. But yeah, does everybody, so this is just saying take the index and add up all the values from 1 to 10. So this is, as Nina said for us, it's the sum of all the numbers from 1 to 10, and Alex added up for us to get 55. Sometimes there's nice formulas for these things. The sum of all the numbers between 1 and some other number was solved by baby Euler. So like baby Euler was born. Comes out, slap baby Euler. Put baby Euler in the crib in the hospital. I don't know what kind of hospitals they had back then. It was probably pretty bad. Put baby Euler in there, and baby Euler then proved the following formula. Before even nursing, this is what happened. Euler was something. So what if I want to add, let's do this here. Let's get a nice formula or two that will help us on Friday. So if I want to add up all the numbers from 1 to n, so check this out. This is just 1 plus 2 plus 3, and I don't know what n is, so I'm going to add all the way up to n. Eventually I'll be at n minus 1, and then the next one will be n. Just like here, n was 10, and here's 10 minus 1, here's 10 minus 2, so you can work your way in from the right-hand side. Let me stop before I go on. Does that notation make sense? Because if it doesn't, none of this. This is all just going to be like Charlie Brown, adult. Wah, wah, wah. Okay. So what Euler noticed was this, and this actually did. Euler was able to speak. I'm pretty sure when this happened, but Euler noticed, and I think this was like in 3rd grade or something, the teacher said, add up all the numbers from 1 to 100. And all the students in the class started going, 1 plus 1 is 2, 2 plus 3 is 6, and started literally adding them up. And then Euler said, wait. If I take up all the numbers from 1 to 100 and add them up, I could write that in reverse underneath. So, right, this would be 2 less than that number. So I'm writing that whole sum in reverse. And notice how they would pair up. You write it in reverse, there's the same number of things in the forward sum as the backward sum, and then you can add straight down. Let's just add these two together. That plus that, what's this plus that?
1 plus n.
1 plus n. What's this plus that?
2 plus n minus 1. So
Which
1
is?
1 plus n.
1 plus n, right?
Yeah,
Again,
and then 1 plus n,
1 plus n,
etc.
Oh, Euler, you've stolen our hearts. Again. Yeah? And this should be n plus 1. I got like excited with the order. The order's the same. How many of these are there?
100.
Well, we don't know. It would be if the n was 100, you're right. N of them. So there are n of these. So that means I could just take one of them and multiply by n, and that's equal 2 times the actual sum, original sum. So the original sum's half of this. One plus 2 plus 3 plus n. So you want to add the numbers from 1 to 10 instantly. So when n equals 10, the sum is, so 1 plus 2 plus 1 up to 10 is equal to 10 times 11 over 2. 110 over 2?
Yeah.
And that is 55, just like you computed for us. What's the sum of all the numbers from 1 to 1,000?
555,000.
Let's-
I'm messing up the zeros.
Yeah, so you're just using the formula, right? So if I say, what is this? So now look, you've got a new superpower. Almost every day you walk out of here with some superpower. You just don't think of it that way, but it is. You're like literally in like the top 1% of math knowledge in the entire world that it's ever been.
It's 500, 500, so 500,000.
Yeah, so let's see. So that's 1,000. I got to do this by myself.
1,001 divided by 2.
And then this is what Nina was working out, so that's 500.
Yeah.
So, oh shit.
It's 500,500.
Okay, that sounds good. 500,000, 500?
Yeah.
Yeah, so that's what you said too, right, Nina?
Sure,
not?
yeah,
Hold
sure.
on,
I was making my way there.
I'm just gonna, I gotta do this myself. Let's see, so we can toss those extra zeros out to the side and just do this. Oh yeah, okay, there we go, yeah, okay. Over 2, no, that was over 2 already. Good. 500,500. Good luck doing that by hand. Like you can come mow my lawn and I'll pay you if you have that kind of time. That would be great. I could use that, or like aeration. I'll buy the aerator and then I'll give you the formula as payment or something. So, nice formula, right? Just totally beautiful. Here's another beautiful formula that we're not going to prove because it's actually a little beyond the scope of what just the time we have and what we talk about in this class. But keep that formula in your back pocket for just to blow somebody else away somewhere in the world in the future when you encounter them. If you go into the business world, you're going into the business world. You go into the business world, you know any math, you instantly run everything. Literally. My friend, I met him as an intern. He was an intern at IBM. He was a maniac. Like, he was like, every weekend he was like crashing his bike drunk into a ditch, getting in fights and getting banned from bars and fights with cops and all this stuff. He is now the richest human being I've ever met. Because he was a math major who knew how to sum an infinite geometric series. And he took this single bit of knowledge and used it to blow everybody's minds in this company, to become a president of this company. And now he's retired at 40. He's done. He's done working. Now he's trying to look like he's not rich so that people still want to be with him. So he's just like kind of like trying to look like he has stuff going on so that it doesn't look like he doesn't have stuff going on, which is a full-time job, apparently. But you know some math, go into business with it, school everyone. Here's some schooling you can give them. If I have the sum, sometimes my sigmas get a little crazy, from I equals 1 to n of I squared, so the sum of squares. So this is 1 squared plus 2 2 squared plus 3 squared. And the good news is, this guy's my best friend in the world. We're like absolute brothers. It's good to know the king. I will tell you that. It's good to be friends with the king. If Regis ever closes, do you know who Cato Kalin is? You don't. He was like this guy who hung out in O.J. Simpson's house. He like just lived there. He was just like, he would live in various Hollywood stars' houses. And he was like a witness to the crime and all this stuff, kind of heard shit. But he just like bummed off of celebrities. I want to be Cato Kalin. This job falls apart. I can't be a math professor. I'm gonna go be my friend's Cato Kalin. I'm just gonna move into a house on his property and like go, what do you need today, brother? Mow your lawn? You got it. Do it. Sum numbers, sum the squares from 1 to n, done. Don't even think about it. I got it. Okay, sorry. So anyway, there's a nice way to do this, and the formula is as follows. And that's not easy. That's not easy to show. But it is true. And then there's the companions for like the cubes and all that shit. We're not gonna, we will need this on Friday. But that's it. And we will meet in person on Friday. Anybody know Kelby outside of class?
Soccer.
Soccer? Do you know her from, you?
I've just seen her on soccer.
Okay, yeah. I just gotta remind her. I don't want her showing up online by herself. So I'll take care of it. So, for example, if I asked what is the sum of the first 10 perfect squares? So here n is 10. And so we've got 10 times 11 times 21 over 6. Really counterintuitive. Let's do some simplification. So I can pull a 2 out of that, so that's 5. I can pull a 3 out of that, that'll turn to 7 times 11. Now the 6 is gone. So 35 times 11 is 385. Done. Like a freaking super genius. But I just know the formula. That's like beautiful mind shit when you can just add that stuff up on the spot. That's it. I think that's enough. This has to sit before Friday. So I implore you, be here on Friday or be prepared to watch the video if you're not. Some heavy shit's going on. You doing all right? Yeah. Okay. Yeah. Hi. Hi. So we should figure out. Did we already figure out a time to get together? No.
I think you sent me an email, but I haven't.
Oh, that's right. Tuesday. I was wondering if next Tuesday would work because it didn't seem Tuesdays are bad for you.
Yes.
Okay.
My schedule is very, very light. I have maybe 10 minutes at a time.
Okay. What are your like the time after this class?
After this class.
Do you have a class you're going to?
No, right now I'm about to go take a test because we have to take tests outside of class time.
Okay, but it's a makeup test.
No, it's just like the test.
So you normally don't have stuff after this class.
No.
We could meet, my friends. We could meet after this class. You could like, if you want, because I have office hours till 2, pretty much after this. So
Okay.
whenever you want, like next Monday.
Okay, yeah.
Does that sound good?
What? Monday.
Is Monday not good? Why don't
I'm
you
just-
send me? Why don't you send me some times that you're
Okay.
free? And on Tuesdays and Thursdays, I can meet lots of times by Zoom,
Okay.
if that will work. But you probably have labs and shit like all day long.
My fun fact.
Okay,
Do you want
let's-
to know a fun fact about my schedule?
Sure.
My Mondays,